So we're jumping into problems involving vector operations. So these are real-world problems. So in the real world, physics mainly, physics loves vectors. We'll consider combined effect when vectors are added together. The sum is called the resultant vector. So an example of this is when you have a big ship, which I've drawn here pretty poorly. So imagine this is a ship and it's pulled by tugboats. And tugboats never pull from straight in front. They pull off to the side. So you would see the two tugboats, one of them is pulling out this direction, one of them is pulling out this direction. Those two forces combine to be a resultant force here. So we're looking at these and we can start thinking of vectors in individual bits to problem solve. So we're going to look at an example from here. So in still water, Jakers or whatever, this is not a name I'm familiar with, can swim at 1.5 meters per second. Jakers is at point A. I've drawn the diagram here. So he's at point A on the edge of a canal and considers point B directly opposite. A current is flowing from left at a constant speed of 0.5 meters per second. So if Jakers dives in straight towards B and swims without allowing for the current, what will his actual speed and direction be? So if we consider this here, now I'm going to let's go to this nice dark one. So we're considering here, we've got a vector already going this way. We've got this current here that's 0.5 meters per second, and that's the current. So we've got to consider how we're going to label this whole problem up. So in this one here, we should consider let current equal C vector, and let's consider Jakers equal J with a thing at the top, and then let's do, I'm going to pick R for resultant vector. All right, so in this first question, it says, in this first part, he dives straight in towards B and swims without allowing for current. What will his actual speed and direction be? So if we consider this, we consider he jumps in here, and let's just do 1.5 is 1.5 squares, so it's about this. And this is the J vector for Jakers. All right, and then not only does he have that, he has the current one operating against him, which is 0.5. So this is the current one, which, is this going to be big enough? Yeah, or should we stretch it a bit? Let's stretch it to make our example a bit bigger. Okay. Will that work there? There we go. Cool. So we've got, that's gone up. So it's just a little bit bigger so we can see it. And so our resultant vector here is this one here, which is going to be our R, which is these two vectors added together. And so in this space, what you have is we have this right-angled triangle, all right? And so when we consider this, we know the two edge ones here. We know J and C, we're given those. So we've looking at this right-angled triangle, we can find out the length of our resultant vector for our, and the length here, this is going to be resulting speed, because this is going to be the two vectors added together, so it'll add his speed together, and that is, if we look, so that squared plus J squared plus the current squared is going to give us all his speed added up, and so we have, he can swim at 1.5 meters per second plus the current is 0.5 meters per second. Now, these are vectors, but obviously we're just dealing with the lengths at the moment. We can actually divide these into individual components for some of the problems, but for the minute, let's just go with this. So these values here is going to equal 1.5 squared plus 0.5 squared is going to equal 2.5 when you put that in the calculator. Therefore, the square root of 0 as 2.5 is going to give us approximately 1.58. And so this means that this side here is approximately 1.58 lengths. So his resulting speed is approximately 1.58 meters per second. Now, I've used speed because it doesn't have direction yet, but we'd actually specify this in a minute. Now, we've got to also pick direction, so we need to figure out what this direction here is. And if we notice, I could use the resulting vector, but I've had to round that value. So we're going to actually pick these two here. And so theta, we've got an opposite and an adjacent. So we're going to use our tan vector, our tan identity. So tan theta equals opposite over adjacent. And on this triangle, our opposite is our current. So we've got current, the length of the current over the length of Jacobs, which means we're going to be looking here at 0.5 over 1.5. And so theta is going to equal inverse tan 0.5 over 1.5, which is going to give us approximately, oh, that's not the best approximately sign, approximately 18.4 degrees. So you can see the current's actually going to pull him off significantly, that he's going to go off at 18.4 degrees here. So even though he's swimming, and now we need to state this answer, we need to state, because when we put these two things together, it's now going to become a vector again. So we're going to write Jacobs has an actual speed of approximately 1.58 meters per second and direction of approximately 18.4 degrees to right of his intended, they've used line there, but aim or something like that. Whatever to say that he's going 18.4 degrees from his intended direction. Okay, so second part, Jacobs wants to swim directly across the canal to point B. So as we know here, the current's going to pull him off. So this means we're actually going to have to swim out this direction to balance this out. So at what angle should Jacobs aim to swim in order that the current will correct his direction? So this is not a bad one here. So we're actually looking at going out this way. Now, I'm not going to draw this to scale because we saw it in the last one. So we're going to look at this. And what we want is we want our resultant vector here to be straight along this line here. And so that means that this 0.5, or the current there, let's use C, and our Jacobs vector, they need to cancel each other out, which we're not really talking about it yet, and this example doesn't really talk about it too much. But if we were considering an XY axis here, this is actually saying, well, we need a negative X component on Jacobs, so the current would then cancel itself. But let's keep doing the way the example's done it. So they've gone, well, now we've set up our triangle. We're going to find theta first. So theta is, we're looking at opposite over hypotenuse. So let's find our direction first. So that's what it says anyway. At what angle should Jacobs swim in order to add the current correct his direction? So we're looking at sine theta equals opposite over hypotenuse, which equals the current length over Jacobs' swimming length, I guess we'd say, which is going to equal 0.5 over 1.5. So theta equals sine 0.5 over 1.5, which is approximately 19.5 meters per second square, meters per second. Okay, and this is to the left of intended line. So then our next bit here is we've got to consider this as a right angle triangle here, all right, where we're looking to find the resultant speed. So we're looking at here, this time we've got the Jacobs swimming vector is going to be equal to the two shorter sides, which is the current squared plus the resultant vector squared, which means because we're going to find the resultant vector, it's going to equal the square root of Jacobs swimming vector minus the current vector squared, which, if we break that out, is going to be our Jacobs vector is 1.5 squared plus, minus 0.5 squared, which is going to equal square root of 2. All right, and then that is approximately 1.41 meters per second is the length of that vector. And so that means, remember we're looking at the length of r here. It means that in this direction towards B, because he's actually swimming out this way, and the current's knocking him back, he's going to be going in that direction there. So that is the problem done. And these are quite long, so just try and pick and choose a little bit here. But thanks, guys.